So now let's look at the different ways of solving them. Okay. So these are what we will call techniques. Okay. So now there are, looking at the equations of Maxwell, you could solve them in, let's say, either the time domain, or if you use Fourier ideas, you could solve them in the frequency domain. Okay. So we will see what these are as we go along. So the other way of solving them is by looking at what form in which Maxwell's equations are written. The form which I showed you at the start of the lecture was which form? Differential form, right? They were partial differential equations. Okay. So I can solve them directly in that differential form. There is another version of Maxwell's equations which is in integral form, right? So we can convert it to integral form and solve it that way as well, right? So now which method to use when? This is really very important, and hopefully at the end of this course you will know which method to apply when. If you don't know that, then life becomes like that person who has a hammer. You know, if you have a hammer, everything you see looks like a nail, right? So you learn one technique and you have not studied other techniques, so you apply it everywhere. We don't want to do that. So I'll give you a simple example. Let's say I have a radar. Okay. Now typically radars, they send a single frequency wave, right? It's sending a single frequency, let's say an air traffic control radar. It's sending a wave, it's hitting the plane and coming back, and we are calculating, let's say, time lag or something to find out how far it is. But it's sending a single frequency. If it is sending a single frequency, then if I substitute, you know, the time dependence of this form, then d by dt becomes j omega. Then all my equations have only spatial derivatives. The time derivatives have gone. Since the time derivatives have gone, my life has become easier. I don't have to worry about time derivatives. It's just become a constant number j omega. So I have to deal only with the space derivatives. So in that case, so single frequency case, it's better for me to work with a frequency domain way of solving these problems. Okay, why make life more complicated? On the other hand, let's say you have a situation where there is some transient response that you are interested in. You turn some switch on, there's some transient thing that happens over there. There, what happens when I have a very short-lived signal in time? What is the frequency content? Very large, it's spread out in frequency. So if I wanted to solve this problem in frequency domain, I'll have to solve for various omegas, then take the inverse Fourier transform and get the time response. So that's like holding your nose this way. So time domain methods would be better for that. Let's say a circuit simulation, you turn a signal on and you want to see how the wave spreads and things like that, right? So there we will work directly in the time domain. Okay, so this is for example, transient responses. Okay. Now, so that is two different ways of looking at time versus frequency. The other aspect is differential versus integral. Now, this may not seem very clear to you in this class, but it will become clear as we go along. But there are a few hints that I can give you. So, when we look at, let's say, the differential form, there is, let's say for example, d by dt is everywhere and d by dx is everywhere. Okay. So, if you were to solve this numerically, what would you do intuitively? If there is a derivative in time and you want to solve it numerically, you would? No. Well, because I am solving it on the computer, I cannot calculate these derivatives analytically. So, I will represent a derivative in time by something like f of t plus delta t minus f of t divided by delta t. Finite differences, that is how I will implement a derivative. Similarly for the spatial derivative. So, when I do this chopping up of space and time into discrete things, what happens is that as a wave travels on a discrete grid, it begins to disperse. You want the wave, so physically I send a wave from here to the end of this room, it goes like a wave. But when I want to solve it numerically, I have to discretize, chop up space and time into finite segments. I can't make it infinitely small, otherwise the memory requirement will go to infinity. So, I take some finite distance, and when I propagate this field, you will see, we will see in this course, that field begins to mathematically disperse. Physically it's going in one direction, but mathematically because of this discretization it begins to disperse, which we don't want. So that would be an example where a differential method is not suitable. On the other hand, integral methods have a very beautiful theory within them which we will study, which don't allow the wave to disperse. So if I have propagation over long distances, over there I should switch to integral equation methods. Now those of you who saw the review lecture on vector calculus, there were two very important theorems, for example the divergence theorem and Stokes theorem, right. So let us just write down divergence theorem. So divergence theorem said that the flux of a vector field is equal to the divergence of, the volume integral of this, right. So closed surface this. Now when I use integral equation methods, let us look at this over here, and let us say I have some volume V over here, okay. So some volume V. Now if I want to solve the system of equations numerically, as I said, we must do this chopping up into small dx, dy, dz, dt. So on the right hand side, I have to chop up this entire volume into small cubes, right. That is what will happen. So this is a 3D problem, but the same thing on the left hand side over here is only over the outer surface. So this is a 2D problem over here, okay. So from a computational point of view, the advantage is that in an integral equation method, what I can use theorems like this to convert a volume integral into a surface integral, and you can imagine that for a given volume, the number of small volume elements will become much larger than just the elements that are on the surface, right. Surface area versus volume, which one grows? Surface remains smaller than volume, right. So okay, let us look at what is the volume of a, let us say take a sphere. What is the volume of a sphere proportional to?
R cube.
Proportional to R cube. What is the surface area proportional to? Square, right. So as R increases, as I go to a larger and larger object, which number is becoming larger? Volume is growing larger. So this, the cost of doing this is going to become more and more, because now little cubes that make up that volume are increasing at a much higher rate than the surface area, right. So these kinds of tricks, they help us to save a lot of computational time, right. At the end of the day, you may have a very good method, but you want a solution that comes to you within reasonable time. No? You don't want to say, okay, I have coded it, I'll come back after 1 month. And usually what happens after 1 month is you discover there was a coding mistake. So that's not what we want. So that's why you will use these integral equation methods, okay. So we will talk about all 4 different kinds of methods in this course, and after you are familiar with all 4, then you can choose for a given problem what is the best candidate, okay. So these are broadly the 3 methods that we will cover in this course, okay. So what is IEM? It is integral equation methods, okay. So this is, so integral equation methods, obviously you can see that they are integral methods and usually formulated in the frequency domain, okay. Then you come to FEM. FEM is finite element. So this is finite element, okay. Any guesses? Is it time or frequency? Those of you who are familiar with it, it's actually frequency domain again. So it's frequency domain. And is it differential or integral? At least the TS should be able to answer differential, right. So it's in the differential form. And finally we have FDTD. So that's finite difference time domain, okay. Basically using this idea, finite differences, right. So this, as the word almost gives it away, this is going to be in time domain and differential form, okay. So depending on whatever is the problem at hand, we are going to use one or the other, okay. So, that sort of brings us to where is computational electromagnetics actually used, where would, where is it useful. So, I have just put a few simple equations of pictures over here to show you simulation results. The credits page has gone from here. These are taken from commercial software like CST, microwave and HFSS. So, for example, the first thing over here, this is, can anyone tell me what is this? This structure over here, it is a horn antenna, right? And what is coming out of this is how is the electromagnetic field that is shooting out of a horn antenna, what does it look like? Okay, so now this is a simulation which was done to find out what the field looks like. Okay, so now horn antenna is known, but now let us say tomorrow for your particular application you build some other antenna and you want to know how does the field look like. Now you will be interested in how the field looks like, because let us say you have a communication problem. I want to communicate from here to let us say that point, and I want to make sure that no field goes to some eavesdropper on one side. So I have to make sure that this big beam over here is only in one direction, not in the other direction. So how will you know it? You have to solve Maxwell's equations numerically and get this. Okay. So that is an example of an antenna pattern. Then here is another interesting example which in technology these days is becoming very important. So this is a collection of many antennas. So it is called an antenna array. Okay. So any of you who are working or interested in 5G, these people will be using antenna arrays instead of just a single antenna. There will be an array of antennas which will be used to do beamforming, MIMO and all of these things. So how do you, again same problem, I want to send a beam here but not there, all of those things. So calculate the radiation pattern of an antenna array. So you would use CEM techniques. The other thing, for example, we hear about a lot is cell phone radiation damage to, let us say, biological tissue. Is it true, is it not true? Well, it is not fully clear, but at least one way to scientifically study it is to build a, let us say, a model of human tissue and then simulate a mobile phone radiation. And then you can see what is the maximum field generated. So scientifically you can say, look, so much field is generated, if it is used for so much time, so much heat will be generated, there may or may not be tissue damage. So that is one scientific way of doing it. So this is a very active area of research. A lot of cell phone companies, that is why employ computational EM people, because before they put a product in the market, they have to certify this produces so much radiation, things like that. And then there are large amount of military applications. So when computational EM started in the 60s, one of the major driving forces were military applications, that you want to make a stealth aircraft. It should not be detectable by radar. Now if okay, that is the goal, but how do I make sure that it is not detectable? I simulate and show that the radar cross section is less or more. So in this simple example, what they have done is they have taken an aircraft and either made it out of carbon fiber or a metallic frame, and this simulation is showing you the I think the electric fields on the surface. So they are different, and therefore the radar cross section is going to be different. So this can be used for aircrafts, ships, any other such missiles where it is needed to know what is the radar cross sections. This is RCS calculations. Okay. These are just some of the applications, and we will look at more towards the end of the course when we look at applications of CEM.